I was really excited about the conference. Um, Tuesday was the day after all of my students had left, and oh shoot. Well, the recording is posted to YouTube and Canvas. Um, Tuesday though, I had the lightest day of my week. Sunday and Monday it was like woke up at 6 a.m., went to bed at midnight both days. Tuesday, I had a 3 or 4 hour workshop in the afternoon, and that was pretty much it. So I was able to finally answer emails, get to the work I needed to do, and then Wednesday I had another wake up at 6, go to bed at midnight, and then actually this morning I woke up at 4, stood in that TSA line for 2 hours. Yeah, I landed at 1:30. It's okay. It's okay. I'm going home. I'm having shorba for dinner, some nice warm Libyan soup. I'm gonna pass out. Milena, we'll see if I wake up in time for class tomorrow. It's gonna be good. All right. Questions from the reagent worksheet. Indigo? No, it's okay. No, that's what I meant. The reaction map. I don't plan on going over all of them, but I can go over as many as you need. I will point out a few things because Jackie showed me hers, and there were some small mistakes that I want to give you feedback on. What do you have any specific questions though on it?
This one.
Yeah, okay, that was actually one that Jackie got stumped on as well. Now, did you remember that that reaction was not necessarily a reaction from this section? Did you look at other sections for reactions? Organometallics, like Grignard reaction? It is not. Um, I want I want you to recognize that the Grignard reaction adds carbons. The Grignard reaction is a carbon-carbon bond forming reaction. So you would have to do acyl addition or substitution of some kind, and now you should get a longer carbon chain. And in that reaction, we lose carbons. We go from a propyl chain to a benzoic acid. So I have cleaved 2 carbons. You're not going to find reagents that do this on the reactions that form aldehydes and ketones or reactions with aldehydes and ketones worksheet because no aldehyde or ketone formed or used. So since we haven't gotten into reactions that form carboxylic acids, we'll get into that next week, then it must be under reactions with alkanes or reactions with aromatic rings. And in this case, it's actually a mixture of both. It's the idea that the benzylic carbon is being oxidized. And what we need here is strong oxidation. Chromic acid looks terrible. Or we can use potassium permanganate boiling overnight. But chromic acid is a little bit, ooh, you know what? It's not better because chromium is not healthy for the environment, but it's faster. And sometimes you have to weigh the difference between putting in energy with something less toxic for 24 hours versus putting in energy for 1 hour with something that's more toxic. Those are the balances that get weighed in the laboratory. Other questions from your worksheet? Okay, good. Yeah, keep looking through other sections. Um, here was one, Jackie, if it's okay that I point this out. Here was one that I saw. We had our ketone from acylation, and we went to, what functional group is this? No, no, but very close. No, it's not a benzylamide. Amide has a carbon-oxygen double bond with a nitrogen attached to carbon. There's no oxygen here. It's one of these new groups. So if it were the imine, and I think a couple of you said this, it would be NH or NCH3 or N-phenyl or N some carbon chain. But the fact that it's CN double bond with NN, it's that NN bond that makes it a specific functional group, a hydrazone. So I want you to think about hydrazine, and I know we don't look at it a lot, but hydrazine is that, oops, that's a weird way of showing it. It's that reducing agent we use. Actually, it was something that you could use here. And hydrazine has that N-N bond. Now, this is simple hydrazine, but you can functionalize it. You can get methyl hydrazine, phenyl hydrazine. You can add carbon chains across it. So having this N-N bond is what makes it a hydras group. And then I want you to think of the carbon-nitrogen double bond being kind of like a ketone, kind of like a carbonyl. That's where I find it recognizable to call it a hydrazone because it's like a hydrazine carbonyl, hydrazone. Now, in terms of the reagent, all we have to do is identify what replaced the oxygen and give two more hydrogens to that group. It's not very challenging to predict the reagent. I'm going to have an NHPH. That's correct, yeah? NHPH. I'm just going to write that as something like this. You don't like that? You can kind of show them both bonded to that hydrogen. And I need this nitrogen, which becomes the hydrazone nitrogen. I need that to lose two hydrogens, which in combination with the oxygen precipitate water from this reaction. So I just need this to be an H2. But this reaction is not very favorable with just a carbonyl and the phenylhydrazine. So we need a catalyst, and we write that catalyst as H+. So that was the one thing that I noticed was missing on yours, Jackie, was the catalytic H+. Do you see that?
Yeah.
Yeah.
Add H pluses to them and augment.
Oh, I am glad that you brought that up. Okay, so yes. Yep. Because they're all essentially derivatives of the same reaction. In fact, I don't think I took a picture of it, but I saw a poster at the conference that, oh, did I tell you about it? That had all of those as just derivatives of this. So you're right. On the reactions with aldehydes and ketones side, oxime and hydrazone didn't have the catalytic H+, but I do want you to have that H+. H3O+ would give us the reverse reaction. That would be not as good. But what the heck is H+? Can you go into a lab and grab a reagent bottle that has just H+ written on it? Yeah. There's actually no reagent bottle that has H3O+ written on it either. Neither of these are things that you'll see written on a reagent bottle. But typically, H3O+ comes from things like hydrochloric acid, hydrobromic acid, sulfuric acid, phosphoric acid, nitric acid. These are largely aqueous-based acids, And those are the ones that you guys are used to using in lab. So in order to have an acid that will catalyze this reaction that doesn't have an excess of water, which would reverse the reaction, we introduce some new acids. And this is going to become relevant in our mechanisms today because there's no one right answer for what you show as the source of H+. We can use things like tosylic acid. And you might remember that tosylate from our leaving groups in OChem 1 reactions. That's actually just para-toluene sulfonic acid. Or instead of toluene sulfonate, they just call it tosylic acid. That's a great acid as a source of H+ because it doesn't need to be dissolved in water. We can also use things like acetic acid. Now, acetic acid does pull in water really readily, but if you use glacial acetic acid, it means that it's without water. It's very concentrated acetic acid. I am trying to think of the other ones that I recommend. Those are what I recommend as a source of H+. In your mechanisms, you're welcome to use TSOH, ACOH as the actual acid source, or you can just show H+. But I want you guys to consider this. What is the conjugate base for TSOH and ACOH? Conjugate base of TSOH? Good. Source of H+, so conjugate base is TSO minus. Acetic acid? ACOH, sorry, ACO minus, acetate. What is the conjugate base? Where'd my block go? What is the conjugate base of H+? Sorry? Well, actually, that's a good one. I want to add that, James. Let's start with what's the conjugate base of H3O plus hydronium? H2O. What's the conjugate base of H plus? Correct. Nothing is the conjugate base of H plus. So if you're showing a mechanism and you have catalytic acid, that means something donates a hydrogen, and then at the end, that thing takes its hydrogen back and is the acid that it was at the beginning. What is it that we show taking the hydrogen back at the end of the catalytic step? Nothing. So we have to show a bond breaking with nothing showing the cause of the bond breaking. There is no conjugate base to take a hydrogen and force a bond breaking. So this is the most challenging to show. But it's not impossible. And I will give you guys an example of what it looks like. But it's challenging, not in terms of how you draw it. It's challenging in how you interpret it as a student, as someone learning the process of these reactions. Because you have to look at a step and say, nothing is going to make this bond break. And that's a confusing sentence because the bond breaks. This bond breaks because of nothing. Nothing is going to make this bond break. Okay? You're welcome to use H plus because you will see it out there, but using some other actual acid is perhaps a little bit better because then you have a conjugate base that you can use to logically think about when these molecules are running around in boiling solvent, what is coming together to cause this change? Other questions from the roadmap? How many of you tried finishing the roadmap? Great. How many of you feel confident in your answers? Okay. Maybe maybe I can recommend that during the break today, you guys take a chance to connect with one another and look at your mechanisms together, or your reagents, and see which ones you differed on and which ones you were the same on and which ones you struggled with that they can help you identify more easily. Okay. There's two mechanisms that I really want to lean into from this unit on aldehydes and ketones. And there is a nearly identical mechanism that I'm aiming for us to be able to get down. The first two mechanisms are acetal formation. Think about what an acetal is again. And acetal hydrolysis. Think about what hydrolysis means. What is an acetal? Can someone share, please? I love that way of thinking about it. Does that help you too? A geminal diether. Geminal, attached to the same carbon. Two ether groups. And what else is going on here? Who knows? Maybe it's a carbon chain. Maybe it's a ring. Maybe it's part of a ring and part of a carbon chain. Okay. What is acetal hydrolysis? Hydrolysis is reaction with water, adding water and reacting it. So formation of the acetal, removal of the acetal, reversing the acetal back to an aldehyde or a ketone. How many steps will I expect to see on your mechanisms when you solve an acetal synthesis, an acetal formation mechanism? Good. No more, no less. If you go through it and you have 5 steps, then you're not following the mechanism, right? Also, you guys understand the basis of mechanisms, that they are not necessarily hard and fast the only way that a chemical reaction will proceed, but they are the most plausible sequence of steps, combinations of bond breaking and bond formations that allow the reaction to proceed. There are very possibly other ways that occur to the very smallest extent, but for the billions of billions, the hundreds of billions of molecules that go through these reactions, these are the most plausible steps. I'm expecting 7, and I'm going to show this with each step really listed out. But you are welcome to pretty much just show that straight down if you want to. And if you're not interested in showing it straight down, then you can flip it and show it straight across, or do whatever you need to do to kind of zigzag around. All right. So we have a chalcone here. Why am I carrying all 18 of them? This is 1,2-dihydroxybenzene. What are we reacting it with? What is that reagent? I'm sorry? It's not a carboxylic acid. Oh, tosylic acid is our catalyst. Yep. Formaldehyde. Lily, what did you say? No, I'm
I don't know. Either.
an ether oxygen. We're not really used to drawing carbonyls as their chemical formula, CH2O. We are familiar with drawing carbonyls as a bond line structure, but formaldehyde is such a small structure that showing it as a carbonyl takes so much longer than just writing out its chemical formula. And showing its assumed hydrogens usually clarifies what we're looking at more. If I didn't show those assumed hydrogens, you would think that I forgot to draw the rest of my structure. That technically follows bond line assumptions just fine, but it's really awkward to look at. So CH2O is the most common way that you'll see formaldehyde, one carbon carbonyl written out. Okay. Jackie, are we looking at acetal formation or acetal hydrolysis? Good. Here's my gem diether, right? And the acetal carbon, the carbon that shares both of the ethers, comes from what carbon? What reagent carbon forms the acetal, Max? Perfect. The carbonyl carbon is the acetal carbon. That's a good thing to write down because that will guide you in your steps. You should always be looking at reacting with this carbon predominantly. Carbonyl carbon is acetal carbon. All right, step 1, acid base. I'm not going to lie, this step can be the most challenging to predict what I should show. First of all, I hope it's obvious that tosylic acid is the acid of the acid base step. That is clear, right? So I want you to ask a question. If tosylic acid is the acid, what is the base? I have no geminal diol. I do have a vicinal diol, but it's kind of arbitrary at this point. Remember that in forming an acetal, I need 2 alcohols. And sometimes those 2 alcohols are connected to the same carbon, different carbons. Sorry, not the same carbon. Adjacent carbons, more than adjacent carbons. Sometimes they're on different carbon chains. So yeah, could the alcohol be the, sorry, could the alcohol be the base? Absolutely could be. Would that help me get to my final product? At some point, I need to get the oxygens that were bonded from the alcohols to bond to that carbonyl carbon. So I think protonating this oxygen will not make it a nucleophile. If I protonate it, I really don't do anything. Nothing beneficial happens in my mechanism. So I don't want to protonate the alcohols. And this is where I want you to pay attention. Acid base carbonyl or at carbonyl. I want to protonate my carbonyl oxygen. This is where I like to think about when you run this reaction in a lab, you've got it boiling on your hot plate, molecules are moving around. let's say that you ran this on a small scale. So you've got 0.01 moles, 10 millimoles. That means that you've got 6.022 times 10 to the 21 molecules. That means that you've got 6 billion molecules. No, I think I still did that wrong. 600 billion molecules. Okay, so you've got a ton of molecules. We are taking a selection of 600 billion molecules. For example, I want you to take a selection of a human. You've got 1 in 8 billion, and you've got a lot of different things that can happen that are similar but different. Same thing happens here, except on such a different scale. So this is, again, one possibility of things that can happen. Elliot said that the alcohols can become protonated. Yes, they can. That does not help me solve for my product. So I'm showing the one pathway. Oh, kind of feels like Doctor Strange in game. And he's like, there are I how many? How many? I went through 14 million scenarios and there is only one way that this works. Same thing here. Okay. Conjugate acid, conjugate base. Again, there's a lot of things that can happen with the products that I form here. But the thing that is most useful, the thing that will actually help me get to my final product. You know, tosylate, negatively charged. It's not unreasonable to think that that is a nucleophile to the carbonyl. But that doesn't help me get to my final product because tosylic acid is my catalyst. So instead, I need one of my alcohols at this step. What should we call that? I know I've already given it to you, but doesn't it look like a reaction step that we've seen already? I have a carbonyl. I open the carbonyl. This is my acylation. Sorry, I said acylation. This is my acyl addition. Max. Yeah, thank you. Can we blame that on me not having my glasses on? That oxygen was not negative. Great job. This one oxygen was negative. Tosylate was negative. Yep. Carbonyl was positive. All right, now at this point, I've got more going on with my structure. I'm going to draw out some of my bonds. I'll be honest, I didn't always do this in my lectures and certainly not on my own work. And when you see this, when I, for instance, have an answer key somewhere and I show something like this, I might not show all these bonds. These two hydrogens I had just previously shown. That's my carbonyl carbon. But now I'm at a point in my structure where I could probably assume those two hydrogens. They're going to be present all the way to the final structure. So if you want to draw these two hydrogens out for every step, be my guest. If you don't want to draw those hydrogens out for every step, you can start assuming them again. So here's what it would look like if you started assuming them. Hey, what is the next step? Acid base. Didn't we just have an acid base step? If I'm proposing to have an acid base step again, actually, you know what? I'll keep those here. And I'll show you here what I show it like. What is my acid? Is it TSO minus? No, because TSOH was my acid. So TSO minus is my base. So what then is my acid? The protonated ether. This is becoming an ether, and it's protonated. The former alcohol is my acid. It's positively charged. It wants to get rid of that positive charge. It donates its hydrogen. It takes its electron pair back. Don't forget that in order for this acid-base step to occur, these two molecules have to run into each other with the orientation that the negatively charged oxygen slams into the hydrogen. So this is why we have it boiling. We increase the chances of those molecules finding each other in the orientation needed to react the way we want. Is that what I called it? I called it deprotonation. I'm sorry. Did I even call the first one? Oh, I'm sorry. Well, now you see that acid base is protonation or deprotonation from a certain perspective. Protonation at the carbonyl, deprotonation of my intermediate. Now that I have reformed my acid, what can I do with it? More acid-base chemistry. Let's protonate something else. What should I protonate? Well, I'm not going to protonate the brand new ether that I just formed. You know why? I'm not interested in going backwards. If I protonated that same oxygen, I just reverse my step. Does it happen? Yeah, all the time. Billions of times a second. Is it something I want to display in how the final product forms? No. Should I protonate the other alcohol that needs to attach to my carbonyl carbon for the same reasons as last time? No, I don't want to. Instead, I'll protonate the original carbonyl oxygen. Once again, this is at the carbonyl oxygen. It's just more challenging to pinpoint because the carbonyl doesn't exist anymore. But we already tracked. We said the carbonyl carbon becomes the acetal carbon. So this primary alcohol I have right now, that is the alcohol that I want to protonate. Protonate, acyl addition, deprotonate. I like to call that one cycle. Protonate again. This time, I'm going to do the opposite of acyl addition. What's the opposite of addition? Do you remember saying that in OChem 1? When I introduced the react. It happens every semester. When I introduce the classes of reactions, I start alphabetically. Addition, what's the opposite of addition? Subtraction. But actually, the opposite of addition is elimination. They really missed an opportunity there. So in this cycle, after I protonate, I'm not going to do acyl addition. I don't have any acyl addition to open. I don't have any acyl group. This time, I'm going to eliminate. What's my good leaving group? If I'm doing elimination, what can I kick off? OH2 is, well, let's clarify a little bit better. OH2 plus. Yep, I'll kick it off. It's got that positive charge, so it wants its electrons back. Am I going to do anything with my TSO minus? It's not unreasonable to think that you might, but actually, this step can happen intramolecularly. The molecule, the functional group, can take care of itself. It doesn't need to happen intermolecularly. I don't need to wait for tosylate to find its way back to this intermediate and run into it with just the right orientation. In fact, in this molecule, it can't do that. But with other molecules, it could. I don't need to wait for that to happen. This molecule will take care of itself. The ether forms a double bond with the carbonyl carbon. I know it's not a carbonyl carbon anymore, but it used to be. And kicks off the good leaving group. kicks off water as a byproduct. All right, if you have been drawing in your hydrogens, then you'll notice that I still have those two hydrogens from aldehyde there. I've just produced my molecule of water. That's my byproduct. That, by the way, in the presence of acid, reverses the reaction. So we've got some equilibrium to compete with now. But I've produced water. I still have my tosylate group. Does this intermediate remind you of anything else, any other set of intermediates or reagents that we have seen so far in this reagent? Is class over? No, we still got an hour. Great. I am sick, man. Time flies when you're doing mechanisms, though. Like, you wouldn't believe it. I'm not going to move on until you identify what it reminds you of. Say it again, James. Have a good night, guys. I'll go home and sleep. Listen, what's the name of the next step? Okay, so where would be a good place to look? It's not funny, Ella. Where would be a good place to look for something that might resemble the intermediate we have right now? At the beginning or like here?
That kind of looks like formaldehyde.
Does it look like formaldehyde?
George, look at that.
It has a positive charge. So does it look like this? It looks like this. And here's my acyl addition step. So is it possible it looks like this? I have what looks like a carbonyl, a CO double bond, and it literally looks exactly like my original carbonyl because those R groups, in this case the hydrogens, they haven't changed. And the oxygen in the carbonyl is protonated. What's the difference between the conditions around the oxygen? Instead of having a hydrogen, it has an alkyl group. It had whatever that original alcohol was attached to. I like to call this an alkylated carbonyl. This is a protonated carbonyl. It's a carbonyl that has an extra proton, positively charged. I like to call this an alkylated carbonyl because instead of an H plus, it has an R plus attached. But it is essentially a carbonyl, so it will go through the exact same acyl addition that we expect. I'd like you to show what will happen for this acyl addition. And the reason that I'm asking you to show this is because I've already given you an acyl addition step. So I want to see you solve it. Please and thank you. And if you'd like to talk with other people and compare thoughts, not graded on this. I want to point out before you miss it, James, your positive charge.
Oh, yeah, yeah.
Perfect. Great job. Now let me see the intermediate that forms. Great. Now let me see that, the intermediate you get. And when you're ready, take it to that final step, do the deprotonation. What did we see last time? Describe what we saw last time with acyl addition. Indigo, I'd like to see on this oxygen, just like on this one, I'd like to see the lone pair. Yep. I know that's you did it here again. I mean, you showed it here, you miss it here. It's like, it's hit or miss. I'm not trying to be nitpicky, but it's those little ones with the consistency. It makes more sense. Can you describe what we saw in the last acyl addition step? Can you look for that same description in this intermediate? Good job, Jackie. Great work, Andy. Thanks for getting on to the next step. You're doing good. If you want to, if you're going to keep with this style, feel free to just start by copying these down because we know we'll need them. Think about what you can describe. What can you see?
So we're gonna break this.
Yes, just like we saw last time.
Right.
And it's going to go that same direction. Good.
Right, and one of the hydrogens are gonna break off.
No, did that happen last time?
No, it didn't. Right.
I do want to see lone pair, lone pair, lone pair.
Okay.
The reason I'm asking to see lone pairs, I call these relevant lone pairs. You are showing an arrow that starts at an atom, but atoms don't go through electron arrows. Electrons go through electron arrows. And the negative charge, that assumes an electron pair. Great. So the last time we did acyl addition,
So then would we actually take the negative charge from the phosphate?
maybe. The last time we did acyl addition, did we take the negative charge from tosylate?
No, we didn't. Not that.
Last time we did acyl addition,
We took
you've got this arrow, just like that. Where can this arrow come from?
this arrow.
Mm-hmm.
It came from the lone pair from that alcohol. Right?
Good.
So then, okay, so then if this bond breaks out, then would that make a lone pair then from here?
Yeah, but where is this arrow? You said this came from, you said it perfect. Say it again.
This came from the alcohol, the lone pair of the alcohol.
So say it again.
Oh, so there's a lone pair from the alcohol.
Nice.
Okay.
See how the lone pair actually helped you?
Oh, wait, so then, yeah, because both these alcohol groups would have a lone pair on it. So,
Nailed it. Oh, okay.
so would it look like this then?
Perfect. Now draw it. Perfect. Now I've got one more arrow. Did you hear that? Can I get that on camera? Perfect. How can you draw it? Hello, hello. This is not what it's doing. This, by the way, is not implausible. It's just not similar to what we did last time.
Like adding something to this, but isn't it just?
I don't want you to think that these two steps are any different from each other whatsoever. So can you describe what this arrow is doing?
Bringing double to get rid of the positive charge in that.
Okay, give me more detail. Yeah, keep going with that. Keep expanding on it.
It's breaking the double bond off the carbon into the oxygen so that it has its electron.
Good. You even gave me more than I wanted so that it has its electrons so that it gets rid of its positive. Can you describe this arrow?
It's giving the electrons.
Keep going.
Does that move through to the oxygen?
No. I mean, like, yeah, in a way, it's a cascading effect. Keep going. Just describe as much as you can. It forms a bond.
It is forming a bond.
Keep using your vocab.
Removing the hydrogen.
Nope. Otherwise, I'd have to have that bond. Maybe. There's actually no carbocation that we're showing. There is a resonance form with a carbocation. Keep going.
Electrons push out double bond.
Electrons to cause the breaking of the double bond. Electrons from describe it again.
Going from
All but ignoring your arrows. You said, what was the first thing you said about the first acyl addition step?
breaking a double bond. Is it making a double bond?
Why don't you break the double bond here?
That's what we're trying to attach, I guess.
Well, don't worry about that then. Just repeat your description here. You started by saying,
Breaks the double bond
and you said you gave more detail.
to the oxygen.
So let me see that.
Okay.
You've got an erasable pen. Oh, okay. Actually, if you want to, this is almost correct. You just forgot the positive on oxygen. Oh, no, I'm sorry. You should have been showing your arrows here. So you actually could erase this for now because we're showing the next acyl addition on this molecule, and I want to see what it forms afterwards.
Okay.
Right? We just formed it. Now I want to see what it does. So you said, I'm not going to say it.
It's breaking to the oxygen.
Not an alkene, but close. Yeah. Breaks the pi bond to the oxygen. Can I see it?
After it breaks.
Perfect. That's all we need to start with. What was the other thing you said?
Alcohol is giving it to the carbon.
What's that? Not an alcohol.
It's okay. It has to take from there.
It has to take from there.
Okay. Does it? Can I just go over there, or does it have to go?
What do you think?
I imagine it just goes over.
It just goes right there. Now it's different because it's intramolecular. I get that. But remember that these molecules don't have to be connected. We're just showing two alcohols attacking. Could have come from anywhere. So alcohol lone pair attacks the carbon, causing the double bond to break. Let me see it. Oxygen lone pair attacks the carbon. Perfect. And it's exactly the same description. CO double bond breaks to O, lone pair from oxygen, lone pair from alcohol attacks the carbon.
Okay.
Tosylate had no role. Tosylate has no role. Now let's just scribble this out and let's see what it looks like.
So is this the structure that would form, or am I skipping?
You skipped deprotonation.
Okay, but this is what I would.
That's your final molecule, yeah.
Okay, so there's something in between.
There is something here that you missed. Think about bonds that were not shown breaking. Your arrows are perfect. Don't change anything.
Okay.
Your product is wrong. Something needs to change here. There is a bond that you have lost that you did not show breaking.
It's the hydrogen.
Yes, it is.
And that's what the deprotonation is about.
That's what we need the deprotonation for.
That one right there.
Yeah, I don't see the OH bond
The OH bond?
because I'm breaking the OH bond, right?
Right.
So I need to show those electrons.
Oh, okay.
This,
You've got the right idea though.
you mentioned there's like lots of other places that can protonate and whatnot.
Yeah.
So is your yield just terrible, or is this the lowest energy state, so it will eventually arrange to this?
Yield is terrible. We can correct for yield by adding in something called a molecular sieve. Perfect. A molecular sieve has holes in it. It's like a little bead. And it's got these microscopic holes that are just big enough for water to get lodged in and trapped by van der Waals forces, which means the water can no longer react in the reverse reaction. So eventually, you form more and more of the product, and that is a lower energy state. And then if you can pull out all the water, Le Chatelier's principle says you can keep shifting it forward to get more product. So, and there are other techniques. You could boil off a product as it forms. But sometimes yield is just terrible. You have to fight equilibrium.
Okay, so when this is forming here,
Yeah.
it's still attached
Yes.
there,
Yes.
and it will still have this hydrogen, like, that's connected directly to that oxygen.
Yes, because that bond's not breaking.
So are we forming a carbon?
No, we're not forming it.
Mhm.
It's already there.
We're just connecting to it? Because then there'll be this H here and this H here.
And that's the carbon.
Okay. And so it just,
So you took the two H's that were on carbon.
Oh, I just.
You lost carbon.
That's cute. Oxygen must become positive.
It will become positive, and it did last time too, right? The alcohol attacked.
Just wanted to double check.
Absolutely.
Thank you.
Good work. Perfect. Nailed it. You got your deprotonation step. Awesome. All right, I'll finish it up on the board. So I think the mic picked this up anyways, but what I got you guys to describe was in the first acyl addition, a lone pair from the alcohol attacked the carbonyl and broke the CO pi bond to the oxygen. A lone pair from the alcohol attacks the carbonyl and breaks the lone pair to the oxygen. I think something that threw you guys off here was that the alcohols were all a part of the same molecule at this point. That's why we were able to make a ring. So this is a cyclic acetal, but there's no reason it has to be cyclic. The other thing that you guys pointed out is correctly, the OH bond doesn't break. So just like last time, I should get a positively charged oxygen. And that is what sets me up. Protonate acyl addition, deprotonate, protonate eliminate, acyl addition. What came after acyl addition? Deprotonate. What is my base? Yeah, tosylate, the conjugate base of my catalytic acid. What is the acid? That protonated ether, that protonated acetal. Okay, so it threw you guys off a little bit. It challenged you that the alcohols were a part of the same molecule, so you weren't sure that they were even allowed to do the same type of thing. But this same structure, what am I doing? This acetal could have formed if the original oxygens came from methanol. It just would mean that my carbon chains don't connect back, so I don't make a bicyclic structure. The only difference between this mechanism and every other acetal mechanism, the only difference do you think you know what it is? Did you memorize this mechanism and be super confused on the final when I give you a different carbon chain? The only difference is the carbon chain connected to the alcohols. Are they two separate carbon chains? For instance, this came from methanol and formaldehyde to give something that was essentially exactly what I had, except my carbon chains weren't connected. That's where I see students slip up the most. They practice and practice and practice and watch the lectures and do the videos and do the worksheet again and again, and they know exactly how to do this carbon chain, and they never see this carbon chain again. They never see me give them 1,2-dihydroxy benzene, and they don't know what to look for. What you guys pointed out today was exactly the descriptors that are present every single time. Protonate the carbonyl oxygen, Lone pair on alcohol opens the carbonyl. Deprotonate that oxygen. Protonate the carbonyl oxygen. This is the most unique step. The elimination step is the only one that is not seen repeated. All of the other steps repeat themselves in this process. The elimination step is the only unique step. Lone pair on the alcohol opens the carbonyl. Deprotonate that oxygen. Done. Okay, can someone please tell me where is the hemiacetal in this synthesis, in this mechanism? A hemiacetal is halfway to an acetal, so that should help you predict where to find it. Yeah,
Yes, OH.
I forgot to draw it. Thank you.
And H2O would also still be there, right?
Yeah, I got rid of the H2O. That didn't make sense. That's why I put it in parentheses. I stopped showing the H2O because it wasn't relevant after that step. And I just didn't want to redraw it if it wasn't going to play a role. But it is. It's produced. And I was telling Elliot earlier, it's the production of the H2O that actually causes this reaction to be reversible. Now that water is present in acid, I can hydrolyze it because that's a source of H3O plus. But if I have something like a molecular sieve, I can pull the water out of solution, and Le Chatelier's principle will shift my equilibrium. If I can boil off water, or if I can boil off my product, Le Chatelier's principle goes to more products. In fact, I used to put over the reaction arrows, so you guys might find this in some resources. I used to put over the reaction arrow. For instance, let's say this. Formaldehyde. No, let's make it more fun. Acetone, methanol, H plus mole sieves, or H plus MS. I will not require you to put that MS or molecular sieves, but you might see it in certain places. And I just want to point out, this is what helps shift the equilibrium. But it's not something that I am expecting you to put on your reagents when you fill in a roadmap, for instance. Helps equilibrium, that's all. Do you guys see the acetal there? Yeah? Acetone, 2 alcohols. I get an acetal. It's just not a cyclic acetal. Guess what? Its mechanism, exactly the same. First, 1 alcohol adds. That alcohol turns into a alkylated carbonyl, and then the second alcohol adds.
When we're saying that, like, if the carbon chain doesn't look exactly the same, are you saying like, or like?
Oh, and you know what? Sorry, I would have typically put on here like 2 equivalences because I need 2 alcohols to make an acetal.
Okay, I'm just meaning like carbon chain, like the.
Here's 1 alcohol, here's another alcohol, and their carbon chains, the benzene ring, are actually connected. Here's 1 alcohol, here's 1 alcohol. That's 2 alcohols. Their carbon chains are just methyls. So their carbon chains are not connected. That's a different carbon chain. Exactly the same. It just might mean, and you guys are done with this, right? So, no, we're not quite done. First, tell me, where's the hemiacetal? Product of step 3? Anybody agree? Yeah? What is the description of a hemiacetal? Half ether, half alcohol. A geminal etherol And that's what we have here. Hemi-acetal. And that is literally halfway through the mechanism. Yeah? Well, it's not. I guess like 3.5 would be halfway through. And that's a little odd. All right. So, what happens when you change the carbon chain? This happens. This is a super uncomfortable way to draw methanol. It's uncomfortable because that is a CH3. I hate it. I'd rather just write out CH3. But do you agree that that follows bond line structure? No, you know what? I could have actually turned those into ethanols. There's ethanol. So if I'm running this reaction in ethanol, oops. Step 1. Yeah. In all of these steps, all I'm doing is just changing the carbon chain. Literally nothing else changes about the mechanism, just the carbon chain. You see it? My partner is going to be so confused about why my finger is so dark tonight after class, because I couldn't be bothered to use an eraser. Of course not. You catching my drift? Hey, it's all the same. I'm dedicated. I'm gonna finish it out. So what do you do if you want to practice this mechanism and John hasn't given you enough carbon chains to draw? Like, all I've given you is this one. What can you do? Change the carbon chain. Take it from benzene to cyclopentane. Take it from ethanol to isopropanol. It's all identical. All right. Now let's reverse it. What is different about going forward from going backwards? Going backwards, every bond that forms needs to break, and every bond that breaks needs to form. So I can actually rename all of my steps exactly opposite. I'll start with an acetal. Oh, sorry. I'll start with an acetal and acid. And Lily actually pointed out, if I am going to do this in reverse, water is incredibly important. Water is one of the reagents of the hydrolysis. Otherwise, it wouldn't be called hydrolysis. I need acetal, acid, and water. And I need to protonate the acetal. My protonated acetal goes through. No. Because I didn't go through deprotonation, did I? I went through protonation. So I don't go through acyl addition, I go through elimination, the opposite of addition. And then I go through, and then I go through, and then everything just reverses. So when you look on the worksheet, do you see, it's kind of hard to see. Step 1 is the opposite of step 7. Step 2 is the opposite of step 6. Step 3 is the opposite of step 5. 4 and 4 are opposites. Step 3 is the opposite of step 5. Step 2 is the opposite of step 6. They're exact opposites. I can go through the mechanism, but you know how to do each and every one of these steps. It's just paying attention to what oxygen gets protonated, what oxygen gets deprotonated, and where your carbonyl carbon is. So I think that if you don't want to wait for me, you can get started on this now. And then you can even flip the page and look at the imine mechanism. What I'm going to demonstrate in for this mechanism is what happens if we don't use an acid and if we just use H plus instead. I know that I've written it there as H3O plus, but I want to demonstrate just for the first couple of steps why it's a challenge to try and use H plus as your acid source. Let's actually have this conversation first. Let's say where the carbonyl carbon is going to come from in the starting material. Do you guys agree that that starting material is an acetal? Is it a geminal diether? Is it? Indigo says no. So can anyone convince us? How do I know where an ether is? The oxygens. ROR, oxygen with carbon on ether side. So that's an ether oxygen, and that's an ether oxygen, and that carbon is a part of both ethers. That's my acetal. What carbon will that be in the product after hydrolysis? It will be the carbonyl carbon. Should I feel comfortable knowing that it is an aldehyde just from the starting material? Yeah. That carbon is only bonded to one carbon. It's a primary acetal. And if it is the carbonyl carbon, it will be a primary carbonyl. Ketones are not primary. Ketones, by definition, have to be secondary. What are you learning from the way that I've written this out? I'm teaching you something without explicitly saying it. Anybody? And maybe I've told you this before, but I doubt it. Yeah, where the hell did all those carbons come from? So you didn't learn it. That's okay, because I implied it. Sorry, that's my same carbon. What I wanted you to learn is that CY is an abbreviation for cyclohexyl. If you don't like drawing out benzene, you can abbreviate it as pH. If you don't like drawing out cyclohexane, you can abbreviate it as CY. All right. Step 1, protonation. What should I protonate? I am not going to protonate a hydrogen. I'm not sure that I can protonate a hydrogen. No, I could. H minus can become protonated and forms H2. I want to protonate. Look at your synthesis of an acetal and go backwards. What do I want to protonate? One of the oxygens. Does it matter which? No. Is it possible that it's one more likely than the other? Maybe. Definitely not in our last case, but these are different oxygens, so definitely could be. But does it matter? No, because at this point, both of them need to be cleaved at some point, and they will get cleaved at some point. So there's more than one correct mechanism here. Which one do you want to protonate first? What's your preference? Left or right? Cyclic or acyclic? On the right? I think that's a good idea because the longer we can keep this a ring, the smaller it's going to be. And if we protonate this one first, it's going to unfold into this chain, and that's just going to be more squiggles for us to draw. Okay, so you'll notice I did put this as H3O plus. I just want to demonstrate for you what it looks like if you're using H plus. You can substitute this by doing what I do with H plus to the hydrogen of hydronium. Oxygen becomes protonated. Oxygen donates a lone pair to hydrogen. Remember, that's the opposite of your last step. In your last step of forming an acetal, oxygen takes a lone pair from the bond. So here, oxygen gives a lone pair to form the bond. Okay, so if you want to do this differently, you are showing the lone pair on oxygen bonding to hydronium. I never draw I never draw two separate things on the same structure as I do that in front of you. So do as I say, not as I do. But I just wanted to demonstrate if you don't want to take this model, this is what it's going to look like. And of course, if you are using this model, that means the conjugate base is H2O. What's the conjugate base of H plus? Nothing. What's my next step? My next step is the opposite of acyl addition. By the way, do you guys want to keep doing this stepwise, or would you like me to demonstrate how this is done fully sequentially now? Is it? You know the thing about fully sequentially? I'll show the arrows here, and then the product, and then show the arrows, and then the product. It's just more cluttered, but showing it step by step takes longer. So there's a compromise between a really cluttered mechanism and just like a lot of writing structures. Do you want to see fully sequentially instead of, I'll still put the steps up. You want to see that way? I think it's better. But if you don't want to, just recognize every time you draw a structure, repeat it, repeat it, repeat it. Okay, here we're going to do elimination because that's the opposite of acyl addition. And because I can't do acyl addition here. Lily? Yeah. Yeah. No, good point. I didn't draw it. No, but not. In fact, I'm not sure what I was thinking. Let's just blame it on the sick. If you want to, you can even show the bond to it. I missed it. Thanks for pointing that out. Why can we not assume hydrogens on heteroatoms? Because that is one of our fundamental rules with bond line structures. You can never assume hydrogens on heteroatoms. Okay, I need to show elimination. What is my leaving group? Yeah, since I don't have OH2 plus, like I did in my acetal formation, this time I want to eliminate an alcohol, not water. Here is my alcohol, the part that's protonated, just like the water was. Some students will give me just this, and then they'll give me a carbocation. It's not what I want to see because we didn't see any carbocations in our original structure. But I know that you guys are familiar with seeing carbocations and you're used to seeing them exist. So why is it that this carbocation doesn't exist? Carbocations are not stable. They don't like to form. But if this can form, why am I not showing it? The oxygen has a better resonance form. Same charge, but full octets. So oxygen holds it so that carbon doesn't have to. So that carbon doesn't have to break its octet. The fact that this mechanism can avoid a carbocation by a resonance structure that is a better contributor to resonance is exactly why this reaction happens as easily as it does. And what do I have here? Something that looks like a carbonyl, an alkylated carbonyl. So what should I do next? If I've got a carbonyl, I want to see acyl addition. What should I have attack? Max?
We do the double bond here to like back to the top.
Good. We know that happens in acyl addition. Oxygen will take the double bonded electrons back. So who should attack? Look at your forward synthesis. Figure out where the opposite is here. What was it that just left that now needs to go back on? We're at step 3, so you should be looking at the acetal formation step. Oh, I'm really bad with math. Step 5. OH. Say that again, Lily. OH minus? I don't see any OH minus. The alcohol should attack? Okay, those seem like the two options. Is it the alcohol or is it the water? So the alcohol should attack, which would give me this. That's not the direction I want to go. So the water. So if you look at step 6, what leaves in step 6? Oh no, step 5. Sorry, what leaves in step 5? Water leaves in step 5. What's the opposite of water leaving? Water adding. See how it is a direct parallel? For that exact reason, I want to point out, when you're preparing for the final, and you know that you'll have one of these mechanisms on there, but you don't know which. If you have one mechanism and you know how it relates to the reverse, you don't need to have both of them. They are exact opposites of each other. Okay, I still have my ring ether. Wow, that's terrible. But now I have OH2 plus. I'm going to draw out both of those H's. I've also got my cyclohexanol. If you have been following along with H3O plus, you also have a second molecule of water here. Okay? If you're following along with H3O plus, you have H3O plus H2O, 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 H2O cyclohexanol, H2O, OH2 plus H2O cyclohexanol. If you are following along with just H plus, in my deprotonation step, I need to show that positively charged oxygen getting its electrons back, just like I see it in every other deprotonation. Here's a deprotonation. Well, I mean, this oxygen's getting deprotonated. This oxygen's getting deprotonated. What is bonding to the hydrogen in order to force this deprotonation? Correct. Nothing. Nothing is bonding to that hydrogen. That's why it's so confusing. Because I am just showing an OH bond breaking to O and leaving now in the world H plus. Right? If OH breaks to O, what happens to H? It now has no electrons. If you're using H2O, and again, that's my recommendation, H2O is that conjugate base. I worry that I shouldn't have done it this way. I'm sorry. There's always something I can screw up on. I don't want you to be confused. So if my arrows are confusing you, talk to me and I'll show you what I'm trying to say. I'll help you clear out what shouldn't be there. Do you guys see where I'm getting at? If you have H plus, nothing takes the hydrogen. The bond just breaks. But if you're using H3O plus or TSOH or ACOH, a conjugate base takes the hydrogen. All right, after deprotonation, protonation. All right, we are now halfway through the mechanism, so I expect that you can finish it. You've already seen a version of this, of every step remaining. So all you need to do is replicate what you've seen. Okay, I'll come around. This is especially the right time if you're confused. Oh, my camera. If you're confused, this is especially the right time to come around. Have me come around and explain what the heck I'm talking about with that acid-base stuff. Did it die? I hope not. It looks like I saved it. But this happened once before. Did I confuse you on this?
I think I figured it out. That's what I was looking
Okay.
at. I don't know.
Because I do want you to show just one or the other.
Yeah, I was like.
Going
I
forward.
can-
Good, good, good.
Okay.
The only thing that I would change here is that you actually don't show the OH bond.
Yeah.
If the OH bond has to break, it has to be shown.
Okay.
You imply it, you've got an arrow that goes to H and then an arrow that goes to O, but that second arrow doesn't start anywhere. It doesn't start at an electron source, right? So you've got the right number of arrows. The only difference would be that bond being shown.
The red is if you only use each black one.
That's right. I think what I should have done was probably more consistently started with this H3O plus being in green. Ah, man, I shouldn't have done it. I should have just done a little excerpt, shown you what happens when H plus. I don't like doing it. I don't like showing two separate things happening because that's not really what I don't ever want to see it. But now I can't not expect to see it on your exams. By the way, this is great for kind of like if you want to come back in and redraw things, you can. But otherwise, if your arrows were just pointed down, it's exactly what I've got. It's just, but it's good. It's great. Mm. All right, so sorry, we're at step 5. You were telling me what?
So
Yes, now I don't want to do the forward. I want to do the reverse of the forward. So you told me what happens in the forward step. Can you say what changes in the reverse? Not looking here. Imagine I get rid of all my reds. And I want to say, this is my starting material. This is my product. What do I do? Yes. And tosylate is playing what role? Generically, its name. Acid. It's just serving as our proton source, our acid. So the acid donates. So the acid. Yeah, and actually not just to the base, right? I mean, you're right, exactly. But what is the base? Because there's 3 oxygens here. Which oxygen does the acid donate to? Again, spot the change this way. Does this change?
No.
Does this change? How can we describe that carbon? Or sorry, how can we describe that oxygen? Yeah. Give it to the ether. Brilliant.
This, so,
Perfect.
okay, so this is just the other product, right, the CYLH.
Yeah.
Okay,
In
so
fact, if you didn't even want to draw it anymore, you don't have to, because it's not going to do anything else.
okay, so we only have the H plus from the deprotonation. Right?
That's right. So, which means I've got acid again. What can I do with it?
You can maybe turn it, you maybe take the lone pair from one of the oxygens and donate to the hydrogen.
Yes.
Okay,
Which one?
so
Because I've got 3 oxygens.
right, well, we did it with this one the last time, so I'm assuming we're doing it with this one.
Okay. That's exactly, that's a great way of going through it. Where's your last mechanism?
Yeah, this one.
Oh, great.
I wrote it on, like, I'm doing, yeah.
That's good. Let's look at the reverse. Here's the opposite of the step that we're going through. Here's what I've got. Because this is my hemiacetal, and here is my
Oh, yeah.
hemiacetal.
Oh, yeah. Basically.
So I want to do this. Last time I did this. I want to do this. Can you tell me, look at those 3 oxygens again, which oxygen gets protonated?
It'd be this one, right? Wait,
Oh, does that go through a change?
no,
Does this go through a change?
no, so it'd be
Does, does it?
yeah, because the hydrogen here breaks off to form a double bond.
Perfect. Well, no,
Well,
you're reading it again
Oh,
this way, but what I'm trying to do is interpret this way now.
yeah,
So what change does it go through?
it goes from an ether
Yes.
to a carbonyl.
Here? Carbonyl has a CO double bond.
Yes, yeah.
Give it to me again. What change does it go through? Doesn't change. Doesn't change.
I'm just gonna,
I don't know. Just throw out some words.
the hydrogen breaks off, right?
Really?
Right.
A hydrogen breaks off? You've pinpointed something about the hydrogen, but is it breaking off a hydrogen?
No, it would be.
Where's the hydrogen?
It's still here.
No, it's not.
No, it's not.
We can never assume hydrogens on heteroatoms. So there is no hydrogen. And then,
No hydrogen. So, okay, so reading from this,
no hydrogen.
and then there is no hydrogen. There is a hydrogen now?
It looks like you've got a hydrogen on your page, doesn't it?
Right, yeah.
No hydrogen.
There is now a hydrogen.
What would we call that process?
Protonation.
Protonation. What step are we on?
Protonation.
So,
Wait, so then,
but which oxygen is this?
that's the ether oxygen,
So what oxygen should I protonate?
the ether oxygen.
Good.
So
You used some really good reasoning to say, last time I protonated the OH, so this time I'll protonate the ether.
right, so it like it looks something like this.
Perfect.
Yeah.
Except you made a 6-member. Yeah, you
so
fixed it. Perfect.
It's like really,
Okay, one thing I wanted to point out actually. You lost your positive charge on this oxygen.
yeah,
Yep. And I think that might have actually helped you see that it was protonated.
yeah.
Because when the positive charge is missing, it's a little confusing. So,
So then this would have a positive charge. Wait. Yes, it would have.
yes,
Charge. And then,
this arrow is just backwards.
okay. Oh, wait, yeah, because the oxygen is giving the lone pair, yeah.
Nailed it, James.
It's because I was thinking about the hydrogen.
Okay, let's see if you can do the elimination step.
That works.
But if they pull some of the carbon by it, then I could see that.
Perfect. Confused by it?
This is way harder than it should be. I don't know why I'm going backwards. It's really hard. It's
Well,
this makes sense. It's just weird.
Yeah, what you're
trying to
saying
figure
is,
out
like the carbon.
Yeah.
right
the
there.
carbon. Yeah.
which oxygen is involved in which step, right? There are
Yeah.
3 different oxygens in this mechanism,
Yeah.
and they each play a different role at different times. One of them gets protonated, the other forms a carbonyl. One of them attacks, one specifically needs to get protonated, one specifically needs to form the double bond.
Yeah.
Once you can name the oxygens
The oxygen.
Well, yeah.
and distinguish them, then the pattern starts to really reveal itself.
This oxygen positive.
I think the first
right here, because you can't really do anything. I can do so kind of have to do this, but it took a while staring at it.
Pick a lone pair, and because this is.
great work. You nailed it. Exactly right. Hi.
Is this what's happening?
No.
Okay.
Is that my final product?
No, there's this stuff here, but like,
No.
is it not going to take the H through here?
Those are the same thing.
We're thinking it's to take from here.
Why?
Since we just took from there.
I don't want to touch this at all. We made this.
Oh, so it would take. We'll go to the other one, right?
Let me phrase this a different way. You guys have correctly predicted or identified which oxygen is the base,
It's.
but you didn't pick the acid, right? Instead of using acid, H3O plus, you decided to try and take a hydrogen from alcohol.
So you take it from here.
Yeah. You remember Cario says charge can help us predict acidity. Positively charged oxygen is more acidic than neutral oxygen.
Okay.
And actually that holds true all the way through this mechanism. Everywhere that you're doing a deprotonation, it's always the more positively charged oxygen that is the acid. And a more negatively charged that is the base.
So I guess my question, I'm just confused, is we just had water. So then we'd be going back to water again, right?
Well, remember H3O plus here is a catalyst.
Okay.
And its conjugate base is water and its conjugate acid is H3O plus. And if it's a catalyst, that means it's going to be involved in the reaction and then reform and then be involved and then reform.
Okay.
I do want to point out your arrow here starts at an atom.
Okay.
It doesn't start at an electron source like it did perfectly right up here.
Okay.
So if you're perfect. Yeah.
If it does take from there, so like for the step 6 or whatever, is it just taking that positive to move over to create the double bond?
Well, positives don't
Well,
move.
it's not moving the positive, but like the electrons are moving to make a double bond.
Let's not forget that so this is exactly the byproduct. This is exactly what we form. Good. This does not form. This, because actually that still has 3 bonds, which is still positively charged. Oh, class is up. Yeah.
Okay.
Remember that step 6 is actually the opposite of step 2, which means I should have this.
Okay.
Do I have that? Do I have an OH?
Yeah, I have an OH.
Do I have a protonated ether? Good night, Milena.
Okay.
Do I have a protonated ether?
Yeah. I feel like you do the piece.
Protonated ether, protonated ether.
Okay.
What should I form?
Feminine di.
No. I should reform alcohol.
Okay.
Never reform an alcohol. And I should reform protonated carbonyl. And that is the protonated carbonyl. But this is still connected. It's not my alcohol.
Okay.
So my arrows need to flow the opposite direction.
But then how did
In the forward direction, the carbonyl oxygen took electrons, which means in the reverse, the carbonyl oxygen needs to give electrons. Yes. It is hard. Yes, yes. Perfect. Perfect. This is this arrow is not
Yeah, that was
not even doing anything. Hey. Ether becomes protonated because I need to make the ether back into the alcohol. Remember, my cyclohexanol is not doing anything anymore. Then I need to run elimination. That is my step 6. What am I going to eliminate? What's my leaving group? That positively charged O. It takes the electrons. Where does my double bond form? Remember, that's what elimination is. Elimination is the formation of a pi bond. Where does the pi bond form? The other oxygen shares electrons. This is now going to be an alcohol. It was an ether. It became protonated. It leaves. It's an alcohol. This is now a carbonyl. On the right, it's just protonated. It's a protonated carbonyl. And by the way, if you are using the green, if you're using H3O plus, you protonated with H3O plus, and you get H2O. And so in my final step, H2O acts as my base. Thank goodness, because I don't want H2O. I want my acid. I want my catalyst, which is H3O plus. And that is my beginning starting material. It's just in a funkier carbon chain conformation. Okay, look at the back. It's a formation of an imine, hydrolysis of an imine. It is one step shorter, which means that there's actually a very similar mechanism, but easier. You just have to figure out how nitrogen plays the role of one of those oxygens instead. If we get time to, we'll talk about it next week, Tuesday, but otherwise we're moving into carboxylic acids and derivatives. Have a good weekend. Keep practicing this. Yeah, derivatives. Huh? No, not like calculus. You know what I didn't say is mapping your carbons can help. In fact, one of the simplest maps that we could have used, you might want to wait for this end to go. One of the simplest maps we could have used was mapping our carbonyl carbon which is where all of the chemistry is really based. And we're trying to get it back to a carbonyl. So I need to get all of the ethers off. I need to get just an oxygen on. So mapping that carbonyl and paying attention to what changes it goes through. All right. Thank you guys for your time.